Alright, you guys, so we're going to do the review of the last section. So remember 6.3, 6.5, and 6.6 will be on your quiz. We had a late morning meeting today, and we were told that you don't have school on Monday, so there'll be no classes. So the quiz is moved, as you'll see on EDSB, to Tuesday at 11 a.m. It will be timed, and I'll be there to watch over you. I know that some of you have school laptops and you had some issues with Flash, so just like the last time, I was there to help you when you did the mock quiz. And you know, that way if anything goes wrong, I can look at the log and see what's going on and try and fix it from my end. So I will be there. If you need anything, just send me a message through EDSB. And I will help you, or I can see if you're having trouble. I can see if you're in and having trouble as well. So, quizzes on Tuesday, 6.3, 6.5, 6.6. So let's go back over 6.6 and do a bunch of examples. All right, so we're talking about the trig form of a complex number, and we're going to go back and forth between the standard form and the trig or polar form. And the things you need to know is that R, which is called the modulus, is the square root of a squared plus b squared. So this is called the modulus, in case you see that word. And then theta is called the argument of z. So in case you see the word argument, you should be familiar with both of those. And you will need them for those of you going to calculus next year. Those are two important words. So anyway, the tangent of theta is b over a, and a is equal to r cos theta, b is equal to r sine theta. And remember that we always go counterclockwise. We swing a ray, we stop. So this is my complex number. I go over some a and up some b, so a in the real, b in the imaginary direction, and I plot my point and I get z. So this is a, and we know from trig that the xy coordinates are cosine theta comma sine theta. So this a here is a combination or a product of the modulus times the cosine of theta, and this vertical distance is the product of the modulus times the sine of theta, or the y coordinate of the point. So let's start out with a simple example, 6 minus 6i. So again, you should always make a quick little plot. We start in the at the origin, going in the real direction. So remember, this is real and this is imaginary. So I'm going to go over 6 and down 6, and I know that my complex number is in quadrant 4, and my theta always goes from the positive x-axis counterclockwise to the ray, which is now a vector. Okay. So anyway, I'm oriented. I know what quadrant I'm in, right? So let's find the modulus. The modulus is just the square root of 6 squared plus negative 6 squared, which is 36 plus 36, or root 36 times 2, right? Which is 6 root 2. So there's your modulus. And for your theta, well, that's just b over a, or negative 1. Now we know in quadrant 1 that the tangent is 1 when the angle is pi over 4, right? So in quadrant 1, if this were you know, my angle where my tangent was 1, the sine divided by the cosine gave me a 1, then my theta would be pi over 4. But we're in quadrant 4, so what we have to do, so remember, relate this with pi over 4, just as a reference. And so since we're in quadrant 4, we have to subtract that from 2 pi. So our theta is going to be 2 pi minus pi over 4, or 7 pi over 4. Now we can take this standard form and rewrite it as z equals 6 root 2 times the cosine of 7 pi over 4 plus I sine 7 pi over 4. And remember, I had said that you could write this in cis form, where you could write it as, it's a shorthand notation. Cis stands for cosine I sine, cis. cosine I sine, because the angles are always going to be the same, so I could write it like this if I wanted to. I'm not sure WebAssign would take that format. That's a more sophisticated format, and we usually use it in places like second year higher level math and IB, because we do some pretty intensive work there. I have never seen it even used in AP, although I teach it, because they accept that notation. Anyway, I don't know if WebAssign will take Sys, so if you have to type something into WebAssign, type it in like this right here, okay? But you could do 6 root 2 Sys 7 pi over 4, and these two things mean the same thing. This is just a nicer way to write it. Let's look at another example. I just have the book open here because I'm just gonna probably take some out of here and be easier, but this number 13 here, 2, you're given 2. That's your standard form of your complex number. Well, what does that mean? What this means is that z is equal to 2 plus 0 times I. So if you need to rewrite it like that to put things into perspective, then do that. Okay? So if I wanted to plot this, I would go over 2 in the real direction and up 0 or down 0 in the vertical direction. So my complex number is right there on the x-axis, or the real axis, I should say. So our modulus is going to be 2 squared plus 0 squared, or the square root of 4, which is 2. Nice and easy. Our tangent of theta is going to be b over a. And we have to say to ourselves, when is the tangent of an angle 0? Well, when the angle's 0. So what this implies is that this happens when theta is 0. So we can say that z is equal to 2 times the cosine of 0 plus I sine of 0. Let's do another one. How about z equals negative 3i? So here in this one, they left off the imaginary part because 0 times I is 0 and we don't write zeros. Here, they're leaving off the real part, meaning that the real part is 0. So again, if you have to, rewrite it as z is equal to 0 minus 3i. So that way when you graph this thing, you start at the origin, you're going to go 0 in the real direction, you're going to go down 3. So again, it's one of those quadrantal angles. And you know that your theta is going to go from the positive x-axis all the way. So this is the ray here. This is your theta. And it's going to stop. So we want to find the modulus. So the modulus is just 0 squared plus negative 3 squared. Well, negative 3 squared is a positive 9, and the square root of 9 is 3. So we've got the modulus. The tangent of theta is b over a. And, don't let that get you hung up, or don't get hung up over that. That's undefined, right? When we divide by 0, that's undefined. And we have to ask ourselves, when is the tangent undefined? Well, remember that the tangent is just the sine over the cosine. So it's whenever this cosine is going to be 0. And the cosine is 0 at multiples of pi over 2. It's at positive pi over 2, 3 pi over 2, and so forth all the way around. So since our angle stops at 3 pi over 2, we're going to say theta is 3 pi over 2. So therefore, z is equal to 3 times the cosine of 3 pi over 2 plus I sine 3 pi over 2. Let's do a few more. Let's see. Let me look in here. I don't know. It's how about 7? Let's do 7. That'll be a good one. So we have 1 minus root 3 times I, And again, if I graph that, I'm going to go 1 in the real direction and down root 3. So my complex number is in quadrant 4, and this is my angle theta. All right. I have to write this in trig form or polar form. They mean the same thing. So I'm going to start out with my modulus, which is 1 squared plus negative root 3 squared. And 1 squared is just 1, and a negative squared is always positive, and root 3 squared is just a 3. So we get the square root of 4, which is 2. So that's nice and easy. The tangent of theta is b over a, right? Or just negative root 3. So again, this is that conundrum, right? Is it pi over 6 or is it pi over 3? Well, again, if you have your unit circle handy, this is the angle pi over 6, and we know that the cosine is root 3 over 2, and the sine is 1/2, and then this is the angle up here, 60 degrees, or pi over 3. And so these swap around, right? They switch. So again, if you don't have this in your little trig book, or you don't have you didn't write down, so you wrote down the sine and the cosine, but you didn't write down what the tangent was for each angle, then again, remember, the tangent is the sine over the cosine. So for this one here, it's the sine divided by the cosine, or the sine times the reciprocal, right? The 2's will cancel, we'll get 1 over root 3, and if you rationalize, you get root 3 over 3. Well, that doesn't match root 3. So it must be this one, right? This would be root 3 over 2 times, so again, the reciprocal, 2 over 1. Here we get root 3. So what I know is that this is a pi over 3 angle. But since I'm in quadrant 4, I have to do 2 pi minus pi over 3, which is going to give me 5 pi over 3. So what we have in trig form is that r is equal to 2 times the cosine of 5 pi over 3 plus I sine 5 pi over 3. Let's see if there are any doozies in here. This one looks good, 23. Let's do that one. So example, z is equal to negative 8 minus 5 root 3 times I. Right? So again, you know, make a quick sketch. I need to go over negative 8 in the real and down 5, so we're talking quadrant 3. Here's my point, and here's my theta. All right, so modulus is negative 8 squared plus negative 5 root 3 squared. Negative 8 squared is a positive 64. Now, remember, don't forget, if you get something like this in WebAssign on quiz day, don't forget to square the outer number and then the radical. So, negative 5 squared is 25 times, right, this is negative 5 times the square root of 3. So this is going to be positive 25 times root 3 squared, which is just 3. And that's going to be 64 plus 75. And so let's see, 5 and 4 is 9, 13, 139. And I would just leave it like that. I think 139 is prime anyway, so I don't think you're going to have much luck finding a perfect square in there. Maybe you can, I don't know. But I would leave it like that. So my modulus is done. It's not a nice easy number like 2 or 3, but it's a number, so I'm good. Now for the theta, the argument. So the tangent of theta is negative 5 root 3 over negative 8, which gives you a positive 5 root 3 over 8. So what you have to do here is, you know this is in quadrant 3. You're going to take out your calculator because you don't know what that angle is. Nobody does. So you're going to do the second tangent of 5 root 3. Make sure the division symbol does not end up underneath the root, otherwise you're going to get it wrong. And divide by 8, and so we get this 0.825. 0.8250, I'll say. Right? But we are in quadrant 3, so we have to do pi plus 0.8250. And when we do that on your calculator, you just do plus the pi key, or the pi symbol. Oh, that's terrible under the light. It's very grainy. And press enter, and you get 3.97. I'm going to round it to. Okay, so what I have is my theta is 3.97. So a weird little angle, but guess what? It doesn't matter because I have a theta and I have a modulus. So I have an argument and a modulus, and so now I can write it in trig form. It's going to be root 139 times the cosine of 3.97 plus I sine 3.97. All right? So I think that's enough examples going from standard form to trig form. Now let's go backwards, because essentially that's all they want you to do in this section. And so there's some really good stuff in here, like finding the roots of a complex number, stuff you would use in Calc 3. Anyway, they omitted it from your curriculum, so no sense in talking about it. Okay. So let me scroll down here to find a couple, and I'm going to move this over a tad. Yeah, perfect. Okay. Let me throw my calculator over there. All right, so let's look at number 25 here. So now, right, so remember that we have a standard form. This goes both ways to trig form. We know that the modulus r is equal to a squared plus b squared. We know that the tangent of theta is equal to b over a. We know that a is equal to r cosine theta and b is equal to r sine theta. So I'm just putting that back there so that way you can keep seeing it. It's important to have these while you're taking your test, since you can take your test with notes or a calculator. Okay, so let's look at this example. We have z is equal to 2 times cos 60 plus I sine 60. All right, and when we had the last homework, and even that little review homework, I had about 4 or 5 students really asked me a lot of questions out of 60, and that's great. If that's accurate, if the rest of you, if the other 55 of you get this, great, okay? But when we had gone over this stuff prior to the review, I had many more questions on going from one form to the other. So we worked on that together. If you ever have a question, I make a quick video and upload it. It takes me a few minutes for it to process here, and then of course it takes a few minutes for ESB to get it uploaded, because I cannot hit the submit button until ESB uploads it, but that's usually not more than 3 minutes. And so then I go over the whole thing and explain everything and work it all out, and the kids seem to be very happy with that. So if you have a question on any of these, do not wait until 11 o'clock Monday night, because I'm not looking at ESB at 11 o'clock Monday night. I'm in bed. I'm sleeping. So, shoot me an email through ESB, and I will help you. Tomorrow is your day for doing work and office hours and practice. So, and to watch the video. So, you'll be watching this tomorrow, hopefully. All right, so anyway, let's convert this thing, okay? I know what my r is. Now look, if you have something like this, and you have a very familiar angle, the cosine of 60, we know what the cosine of 60 degrees is, right? It's 1/2. You can rewrite this, write it as 2 times 1/2 plus, what's the sine of 60? Well, that's root 3 over 2 times I, right? You see what I'm doing? I'm just moving the I to the other side. Why? Because I can already see Z equals A plus BI, right? The only other thing I have to do is multiply this 2 to each term. When I multiply it to the 1/2, the 2's cancel and I'm left with 1. Plus, when I distribute this term distribute the 2 to the second term, the 2's are going to cancel and I'm left with root 3I. And I'm done. That's it. Alright, so that's a really simple example. And, you know, I could have looked at this. I know where 60 degrees is, right? It's a quadrant 1 angle. And, you know, I know that my modulus would be 2. So anyway, I know I'm in here somewhere. Something like this, right? This is 60 degrees here. Or pi over 3. So it makes sense that if I go over 1 and up 3, I end up in the same spot. So anyway, super simple to do. Let's see. Let's do number 27. Z is equal to root 48 times the cosine of negative 30 plus I sine negative 30. Okay, so first and foremost, I want to remind you something, that 48 has a perfect square number in there. And if that's the case, you're going to have to simplify. You always have to simplify radicals. So what I know is that 48 is 16 times 3. So I'm going to write it like that for a second. And again, if you didn't know that, you know, you could start dividing 48 by 4. You can see that 4 goes into 4 once and it goes into 8 twice. So it's 4 times 12, right? And that the square root of 4 is 2, so the 2 comes out, and then 12 is still a composite, so you can break that down to 4 times 3 and pull out another 2. But rather than go through all that work, I happen to know that 16 times 3 is 48, so you take out the biggest perfect square. Alright, anyhow, the square root of 16 is 4, and 3 stays under the radical, so we've got 4 root 3. Now, what do I know? Alright, I know they're talking about the cosine of negative 30, right? And negative 30 is when we go clockwise, so we start at the origin, we go clockwise, we go this way. But that doesn't matter. What matters is I know also what the cosine of 30 is. The cosine of 30 is root 3 over 2, right? But, so, let me just put that, root 3 over 2 plus I times the sine of 30 is 1/2. Now here's the deal. Negative 30 is in quadrant 4. The cosine is positive in quadrant 4, so therefore I don't have to change the sign on that. But the sine of 30 is 1/2 in quadrant 1. In quadrant 4, the sign is negative. So, you know, I need to kind of do that, right? And I'm just going to rewrite that so it's in the form A plus BI. Oops. Minus 1/2 I. Now, you got a little bit of arithmetic here. So I'm going to kind of do this separate, right? I need to make this Z equals A plus BI. I cannot leave it like this. So I need to multiply the first, this constant multiple to the first term. So what I have is 4 times root 3 times root 3 over 2, which is 4 times root 3 squared over 2, which is 4 times 3 over 2, which is 6, right? 2 goes into itself once, it goes into 4 twice, 2 times 3 is 6. So A is 6. For the next product, I have 4 root 3 times negative 1/2, which is negative 4 root 3 over 2. So I know that some of you have trouble with multiplying fractions. Remember, you just multiply the numerators together. So if you have to, put that over 1. And all I'm doing is multiplying straight across on the top Okay, negative times 4 times root 3 gives me negative 4 root 3. And I'm doing the same thing, multiplying straight across on the bottom. 1 times 2 is 2. And then I can reduce it. 2 goes into itself once, it goes into 4 twice, so I'm left with negative 2 root 3. Right? So I have my A here. This is my A. And this thing is my B. So I can say Z is equal to 6 minus 2 root 3 times I. And I'm done. Let's see what else is in here. Well, let's do 34. Because it has a weird angle. So in 34, you're given 10 cosine of 2 pi over 5 plus I sine 2 pi over 5. And, you know, you may say, well, I don't even know what quadrant this is because I don't know what 2 pi over 5 is. All right, maybe not, but it's easy. You know how to convert from radian to degree form, right? So that'll give you an idea. And this is going to be a quadrant 1 angle. But anyhow, if you have to do this, take the angle and multiply it by 180 over pi, right? The pi's cancel. 2 times 180 is 360. If we divide that by 5, we get what? 6, 7 is 35, 2. So 72 degrees. So it's definitely a quadrant 1 angle. It's at 72 degrees, so something like this. 72 degrees. My complex number is here. And I'm not telling you that to convert it to degrees so you can use degrees. I want you to be able to orient yourself in the plane so that way you know what quadrant you're dealing with, whether your sine or your cosine should be positive or negative, yada, yada, yada. All right? And anyway, I may not know what that number is, you know, off the top of my head, cosine of 2 pi over 5, but I've got a calculator, right? So here's where the A and the B equals R cosine, R sine theta is going to come in. We know this is our R, right, 10. So we can say that A is equal to 10 cosine 2 pi over 5. And all you have to do is put that thing into your calculator. And since it's quadrant 1, you don't have to worry about subtracting or adding to pi or anything like that. I'm just going to do 10 cosine of 2 pi divided by 5. And I'm going to get 3.090. Alright, I'm going to do the same thing for B. That's 10 times the sine of 2 pi over 5. So I'm going to do 10 sine 2 pi divided by 5. And that's 9.511, I'll say. Alright, so guess what? I have my A, I have my B. All I have to do is Z is equal to A plus B times I. That's it. Let's see. Ooh, 29. I missed that one. Let's do that one because that is a fraction. Ooh, fractions. Let's see. 29 is 9/4 times the cosine of 3 pi over 4 plus I sine 3 pi over 4. And right away you should know what that angle is, right? From your unit circle experience. You know that the cosine, you know that 3 pi over 4 hopefully is in quadrant 2. The cosine is negative there and the sine is positive there. You also know that any multiple of pi over 4, the sine and the cosine take on the same value. They're root 2 over 2. They're just going to change in sign depending on what quadrant you're in, right? So I'm definitely sure here that this is my quadrant 2 angle, right? So all I have to do is 9/4 times, so remember 3 pi over 4 is going to be, well actually do it like this, do A is equal to 9/4 cosine 3 pi over 4, and b is equal to 9/4 sine 3 pi over 4. Well, you know that the cosine of 3 pi over 4 is root 2 over 2 negative because it's in quadrant 2. So this is 9/4 times negative root 2 over 2. And this one's going to be 9/4 times positive root 2 over 2. Now we've got to multiply, right? So once again, it's 9/4 times a negative root 2 over 2. If you have to write it like that, do that, so that it'll help you remember that you multiply the numerators straight across and the denominators straight across. There are many of you that are very deficient in multiplication of fractions. So if adding and subtracting, unlike denominators, is not bad enough, you can't multiply either. So again, you'll have your calculator, just be careful with it. This is going to give you negative 9 root 2 on the top, and 4 times 2 is 8. So A, because that was our cosine theta, is negative 9 root 2 over 8. And for B, well, it's just going to be the positive. It's 9/4 times positive root 2 over 2, which is going to give you 9 root 2 over 8. So we would write our complex number as A plus B times I. Always write it in standard form, in this form. Let's see, we'll do one more. Oh no, let's do this one here underneath 29, number 30. Again, it's another weird little angle. So in number 30, we have 6 cosine of 5 pi over 12 plus I sine 5 pi over 12, right? And again, I may not know what 5 pi over 12 is. If you want to orient yourself, take the 5 pi over 12, multiply it by 180 over pi, cancel that out. It should be in quadrant 1 because 5 divided by 12 is pretty small. And let's see, 180 times 5, right, divided by 12 is going to be 75, so 75 degrees. So I know that my complex number is in quadrant 1. My theta is going to be some little theta there, right? So again, A is equal to R times the cosine of 5 pi over 12. I'm going to just throw that into my calculator. R is 6. R times the sine of 5 pi over 12. Both of them are going to take on positive values because they're in quadrant 1, so nothing weird to deal with, no adding, subtracting from pi. And if you put that into your calculator, whoa, so we're going to have 6 cosine of 5 pi divided by 12 is 1.553. So I'll call it 1.553. And then if I do the same with the sine, 6 sine of 5 pi divided by 12, I'm going to have 5.79. Move that over. So I'm going to call it 5.796. I've got an A, I've got a B, I know my standard form, so Z is equal to 1.553 plus 5.796 times I. And that's it. So I did a lot of examples on the PowerPoint, on the agenda that I put up for you, actually. I'll bring it up here again. Let's see. This is yours. I'm going to move this over here. I'm going to make this smaller too. So what I'm suggesting is that you open up your textbook, page 445, and try these practice problems. I will post the, not the solutions, but I'll post the answers for you on ESB so you can make sure you're on the right track. If you have any questions from the prior two sections, any of that practice, so like I said, kids already on that last practice, they emailed me, and I like that, so do that. again, don't wait till the last minute. And you have to remember that on day 2, I've got 80 kids preparing for a calculus exam that's going to take place in less than 1 month. So day 2s are crazy for me. If you get a response back from me on a day 2, you're really lucky, because it's that busy. And on day 1, I have to be specific because I have you guys, and I have BC Calculus, who is also taking an AP exam in less than 30 days. And so anyway, I've got to talk to them a lot and go over things with them a lot for the exam. So try and get me during my office hours, but don't wait until, you know, the day before homework's due, or the morning that homework's due, that kind of thing. That should not be happening, ever, okay? So send me an email. I'll be more than happy to help you if you have questions on this or anything in the last 2 sections. This video, of course, I'll link it into Edsby. And if you have any trouble at all, please don't hesitate, and please don't wait, because you know, you guys are scheduled to go to calculus next year. That poses us that teach pre-calc with a whole new set of conditions, because we don't want you in calculus if we can't finish this curriculum, because you're going to be deficient in many things, and we don't have time to reteach you the deficiencies in calculus. By the time you get to calculus, it's expected that you know this stuff very well. So, you know, things are going to change next year. I don't know whether we're coming back to school this year or not, but we are still behind in curriculum, and I need to keep up with the curriculum to ensure that those of you who are going to calculus have the background that you need to be successful in calculus. Because if you don't have the background, you're not going to be successful in calculus. That's how it works. Kids are really, really good in math until they hit calculus, and suddenly it's like, ooh, this is not what I'm used to. So it's really important that I keep on my curriculum. So let me know what's going on, because I'm going to keep moving on once this quiz is over. And we are going to try and get all the material covered that we need to cover by the time we either return to school, by the end of school, whether we return or not, whether it's online or whether it's in the classroom. All right, so have a great rest of your day. Let me know if you have questions, and I'll talk to you later.